Is relational power. This is a 30-minute talk. Please, at the end of the talk, don't exit until the questions are finished. Thank you.
Well, good morning, everyone. Something we all deal with when storing data is the fact that what's called in the biz denormalized data is very tempting. Just sticking into some single container everything that a web view or an API needs as a single chunk means that you only have to hit a single bit of your data store in order to fetch it back. And it makes it very easy to shard and scale reads, right? If everything that a particular web page needs is stored one place, you can put it on any server you want, and the web view only has to reach that one server and it can build the answer. But of course, it makes writes very costly. If we were to store the IMDb, for example, in MongoDB this way, where each movie literally listed the actors inside of it, that would make it very quick to render a movie's web page. But if we needed to correct the date of birth or name of an actor, it means that we would have to run through every single movie they had ever been in order to update that information. On a site like IMDb that's read far more often than it's changed, that's often reasonable. But on sites that need to be a bit more flexible, we will often do what's called normalization, which basically means removing repeated data so that each little bit of data is only expressed once. That leads to, you might still want to use a document database like MongoDB, but, I'm sorry about that. But you might do something like this. Instead of literally storing the actors inside of the list of actors, you might store IDs instead. That way each actor only gets stored a single time. It's easier to update them. You use less storage space. But of course, the penalty is that you've got to pull data together from several different places to draw the IMDb page for inception. A relational database takes this process, denormalization, to its logical extreme. By design, tables have a fixed set of columns. No composite data types in pure SQL are allowed. You can't have inline lists or sets or anything like that. Every single record of data has to have the exact same fields as all of the others. In order to therefore solve a problem like movies and actors, where you need a list, you need for a movie to have several actors, you wind up creating up at the top what's called a binary relation, a third table that's just there so that movies can have a list of associated actors and going the other way through the role table so that an actor can be in several movies. Because there is no composite data type within a column, you can't go into the entry for sleuth and start sticking multiple actors in there. If you see a data design where that movie table starts growing an actor 1 field and an actor 2 field and an actor 3 field, that means that someone doesn't understand the relational database. What are the consequences of this design? A view, in order to render a page showing a movie, often now needs to do several reads from your data store. But note that it makes writes almost incredibly scalable, jumping back one slide, because the presence of an actor in a list of actors or a movie in a list of an actor's movies becomes an atomic operation of adding or deleting a row. Operations to our collections suddenly become atomic, which makes writes very cheap. You don't have to rewrite and restore the whole list just to add one element. So, given that relational databases atomize our data into these tiny pieces, how do we pull it back together? And that's why relational databases have to support a hefty query language that supports some form of the relational algebra so that we can pull everything back together. If you've seen SQL code before, it looks something like this, where you say what fields you want selected from what tables, and you tell it, I'm looking for, the movie's ID should match the movie ID in the role, and the actor ID should also match. And then having described how you weave your tables together to build more complete forms of information, you then have a where clause expressing what particular combined piece of data you want to fetch. Now, in order to understand database design and indeed much computer system design, you need to know that storage is slow. And so it becomes very important to know how to gather several pieces of data efficiently, especially when data is denormalized and you've got to go grab a lot of pieces. The answer here is that indexes, as we'll see in a moment, save the situation by letting us quickly jump right to the pieces of data we need, right to the actors that are in inception, no matter how widely scattered they are through the actors table. But it means that the query plans, the process by which you go and grab just the right rows you need, become quite complex. So to understand this, to start with, you have to understand how slow computer storage is. There's a wonderful blog post, What Your Computer Does While You Wait, that posits, all right, your CPU needs to get information, read and write blocks and bytes of data. Let's, as an analogy, imagine the on-die level 1 cache as being like looking at a piece of paper on a desk next to you. It takes 3 seconds to read the bit of information you need. Given that scale, the L2 cache, which is a much larger data store, but that's a bit slower to get to, would be like pulling a book down from the shelf and taking 14 seconds to find the information you need. Having to go to the RAM chips on your computer, which is like this incredibly slow array of it's like steampunk, it's like a bunch of capacitors, is like walking down the hall for 4 minutes, talking to people to get the information you need and coming back. And then finally, to go to disk is like leaving the building to roam the earth for 1 year and 3 months. You have to understand that scale. Well, first, just to understand why your web browser loads so slowly the first time, but so quickly the second time, and also to understand why it is crucial we hit no more disk blocks than necessary when doing database queries. Disk access must be minimized. You might think, well, why can't we keep our data store sorted and use a quick binary search to jump to what we need? But that makes it too costly to insert new records. You know, the routine, a new actor whose last name starts with A comes along, so you've got to move over all of the other actors to make room for it. And you can only sort by one attribute anyway. If you might want to look up actors by name and birth date, you can't very well sort the whole collection by both at once. So we use indexes. We don't even try to keep tables sorted. We let rows just appear in whatever order they want to, and we get to the ones we want by building a tree on the disk, where we only have to hit a few blocks of some sort of binary tree in order to get to our data. Now, you might be thinking the obvious question, well, wait a minute, Brandon, you just told me how expensive a disk head seek is. If when I want to go grab the movie Inception, I have to first go to the index and traverse it, and then go over to where the table is stored, doesn't that kill performance, right? Because I'm going to have to go fetch a block from one place on the disk, then wait forever while the disk head slowly moves across, and then fetch the block from the table. And if I have to do that, say, 1,000 times, because 1,000 requests arrive, won't it take 1,000 times longer? It turns out it doesn't. Modern operating systems do something clever, where if they're hit with 1,000 requests for disk access at once, they sort them and then satisfy them with a single swing of the disk head across the platter surface. Still gets a bit slow, because once the head is in place, you have to wait for the slowly rotating platter to bring the data you need underneath you. But as you load, but it means that performance at least doesn't degrade linearly. Grabbing 1,000 records simultaneously is actually not even close to 1,000 times slower than grabbing one record, because the modern OSs do such a good job of thousands of block requests are coming in at every moment, and they're just patiently swinging the disk head back and forth, getting everything that's needed at the moment with a single sweep. And that's why we can keep using our databases and computers. Another property to understand is that relational databases actually always append new data to the end of a table. They never try to go back in and overwrite information for two reasons. One, it's too slow. And by the way, they do this even if you are updating a row. You might think that updating an existing row would actually go change it, but nope. They write a new copy of that row to the head of the table and then go invalidate later the row that is now out of date. This provides incredible speed because during a heavy period of writes, the disk head can just sit there writing block after block after block to the same track on the disk. And it also provides what databases call transactions, where you might want to do several, update several values in your database and have it go live at once. That's done by appending the new values you're writing, and then if you cancel the transaction, it just never marks them as live. And the old copy of the row further back in the table remains the authoritative one. So, given that background on how relational databases work, how can we write our code in Python so that we play to the relational database's strengths? How can we optimize our code? The key that I have found is learning to code so that when you need a complex set of data, you only ask the DB a single question, and then if that single question you're asking is running kind of slowly, learning to run explain and adding indexes until it becomes fast. What do I mean by asking the database a single question? Simple queries are very obvious. If I ask for the movie named Inception, the database, if a title is indeed indexed, will use the index and find it. But it becomes a little more complicated when we're doing the normal relational database thing, pulling together a wide variety of information to get a movie and all of its actors, or in this case, any actors born in 1974. We're pulling together several tables, and it's not obvious. Should we go to the movie table, find all movies named Inception, go through the roll table to find all of the actors that played in Inception, and then just manually throw out the ones that weren't born in 1974? Or should we grab all actors born in 1974, find all of the movies they were in, and look through that list by hand for Inception? The answer might seem obvious. You want to go in through the one movie named Inception, but notice that the syntax here is just field equals value, and unless you have special domain knowledge that there's probably very few movies named Inception, but a lot of actors born in 1974, to the computer, these two might look like equivalent approaches. So, a good relational database will do a superb job at what's called query optimization, which is to make precisely that determination that few movies have this title, but a lot of actors were born in 1974. Postgres will have this same knowledge that you do about your data. Other databases don't do as good a job, in my experience, even though all of them have some form of what's called analysis or analyzing your tables. But Postgres will just keep statistics on what the most common values in a table are, whether the table has one value or many, and if you ask your question in a single piece, giving it the possibility of several ways into your data, it will make stunningly good decisions about which way to optimize the query. A good relational database keeps statistics on the distribution of values in every column of every table, so it can choose from among the fastest ways to answer your query again, if you ask the whole question as a single query. If you ask the way I just showed you, it can be optimized because all possibilities are open to go in through the actor's year of birth or through the movie's title. But this cannot. If I have written my code so that I look up all actors by their year of birth and then look up the movie and then maybe grab all of the rows that match both of those sets of IDs, then I have eliminated up front the possibility that my database might be able to do things more efficiently. But wait, I hear you cry. Why would someone write so many tiny queries instead of just asking the big question? And the answer so very often today is because they're using an ORM, an object relational mapper, but they've never learned about joins. They're scared by this whole query business, so they learn the simplest call possible to pull objects from the database and try to survive forever with nothing more complex than single model calls to query filter by. Then they try to jump over to the associated objects with attribute accesses. So they write code like this, where they grab all the actors they're interested in and then iterate over each actor's list of roles, and then look at the movie that that role is associated with and do print for the actor's name if the movie winds up being Inception. This is what I call the O error. It's thinking that you can take the O part of ORM and ignore the rest. It's assuming that object relational mapper, I mean, what's that? It must obviously be a magical word that means a relational hider / concealer / absolver. A mapper, I mean, surely a mapper gets me out of the business of the thing being mapped to completely. I hate to break this to you, but a mapper simply maps things. It maps relational concepts into a non-relational language like Python, not so that those concepts go away and become invisible. A mapping makes things visible and manipulable within the new syntax that's being mapped to. When you're using an ORM, you still need to understand relations, at least a little bit. So, what's the point of an ORM? Why use an ORM if you're still going to have to understand relations, which is to say, to turn this around to the positive direction, what should you be expecting when you sit down with your favorite ORM that it will accomplish for you? What's it good at? What does it make easy? The first two things I'll mention are syntactical. You can get to the fields of a table row, like a movie's title, with beautiful Python object attribute access. You can access relations, all of the actors in a movie, as though the movie just has an actors list attached to it. A very neat thing is being able to build a query by building up lots of little qualifications. You can build in whatever order you want all of the qualifications, and then magically when it's time to run the query, it will swap everything around and put it in the syntactical order that SQL expects. And a good ORM will provide you with something we'll talk about in a minute called a unit of work. In other words, and here now turning to the first issue of syntax, what I mean is that an object relational mapper lets you turn code that looks like that up there on the top, where you're having to embed raw queries in your code and do tuple or dictionary access to get at the attributes of the movie stored in its row. It lets you turn it into something that means the same thing, because it's a mapping, but that lets you use a beautiful Pythonic and object-based syntax to get at your information. So I suggest the following game plan if you're going to be using an ORM and a relational database. Play around and gain some basic select and join skills so you at least have a picture of what's going on in the background. Learn then, in your ORM of choice, how to express a join in Python, how to get a query on one or more objects and do some filter bys and order bys, and the basics of writing in your ORM the same select statement you played with at the command line. Learn your database's explain statement so that you can get some picture when a query is taking a long time of what crazy order the database thinks it should be hitting the actor and the movie in order to put your answer together, and play around with some simple examples. I have on GitHub the exercises from my SQL tutorial on Wednesday. They might help you take you through some simple examples. And you might learn how to fix by, adding an index on movie title. Suddenly it doesn't have to read the whole movie table to find Inception. And kind of learn how that process works. Use logging. When you're connecting through SQLAlchemy, there's a echo equals true you can turn on when you want it to print the queries it's doing. Sometimes I go into a Postgres database and just for a moment in its conf file, turn on logging and suddenly the site slows to a crawl and then I turn it back off. But I now have thousands of queries with their timing in a log file that I can start stepping through to see what's taking a long time and bogging things down, besides my logging. Here's what an explain looks like in SQLite, which is a great database to play with. It's not that smart about knowing whether the movie title or the actor's date of birth will be more highly selective, but it does at least know when to use indexes, and you can play with creating and deleting indexes, looking at the output of explain, and seeing how the same query will be solved different ways depending on what resources you give the database to solve it with. Learn to identify some common patterns. Very common problem is what I will call cavalier access of an attribute that just by touching it, if only you knew, goes and kicks off a new query. Here I grab all the movies in 1981 and look for one-man shows or one-woman shows that had only a single actor or actress. This innocent-looking loop, because movie.roles means that we have to go query another table. This generates at the database level, select all fields from movie where the year is 1981. That comes back with a series of movie IDs. And then every time you hit one of those .roles attributes for the hundreds of movies made in 1981, you do another round trip to the database to fetch its roles. And again, logging will show you, give you a hint that you're probably not doing something right in your Python code. This pattern is solved by doing what's called an eager load. You tell, in this case, SQLAlchemy, hey, while you're talking to the database, getting the movies in 1981, go ahead and have it deliver to you using a join all of the roles that were in those movies as well. And that can reduce to a single round trip to the database the cost of getting what can be a very large set of data. And very often what kills you isn't waiting for the data to arrive. That's often very quick. It's the latency of waiting as the request slowly arcs out over the network and then waiting for it to come back. The eager load lets SQLAlchemy, and this goes back to my statement about try to ask single questions that get you all the information you need. The eager load lets SQLAlchemy know everything you need in one statement ahead of time. Another pattern is aggregating all of the different conditions. This is the same query we looked at in SQL earlier. It's how in SQLAlchemy you would go ahead and with a single statement tell the database your whole question so that it can optimize it. Final thing is an outer join. Going back one slide, something you'll notice here is this will give us movies in 1974 that had Sean Connery. But sometimes what you want to do is show all movies in 1974 and then, like, you know, have blanks next to them unless they had Sean Connery in them. And one of the annoying things about a join is that it throws out members of either table that don't have a match. The solution is something called an outer join. An outer join keeps all matching rows of the left table, whether they have a corresponding match in the second table you ask about or not. So this would return every movie in 1975 for you to display on a web page or whatever, and then if one of those movies had, or if several of them, had a role named Batman in the movie, that information would come back paired with the movies that had that. An ORM makes using a relation look native and pretty in Python. I went over a nice little list a minute ago of all the advantages. But I should admit, ORMs do tend to introduce complexities and surprises of their own. So in payment for having this beautiful syntax for doing selects and queries, you will often find a few little headaches or edge cases. Two example surprises that I often see people run right into are that the Django ORM lacks a unit of work pattern, and that SQLAlchemy possesses one. A unit of work pattern is careful to make sure you only pull one copy of a given database row into memory. And so what happens with Django is people will, on an admin page or something, pull in 2 lists of users, go update everyone in the first list to reactivate their account and save them, and then in the second list promote everybody to an admin and save them. And if there is a row like a user that turned up in both lists, because that's 2 copies of the user, the second save overwrites the first one. Because there's no unit of work, there's no concept that we should map a database row into a single in-memory object. And then I've seen people get bitten by the fact that SQLAlchemy does follow this pattern, which happens when I had a client who they kept hitting reload and kept seeing old data on the web page, and it was because the unit of work was serving as a cache to keep old objects that had already been pulled in intermediate results around, even when they had moved on to something else and really intended to start fresh. Let me admit, you might not have guessed this, but I'm excited about NoSQL because for the first time in a long time, I see programmers sitting down and reading database documentation and actually understanding it. After all, I mean, if you think about it, the first breakout hit database among web programmers was, after all, a NoSQL solution. We have a long history of this. It was called MySQL. If you go back and look at the first version, it had no transactions, no joins, no subqueries. That's NoSQL. But it caught on like wildfire because it was what people needed. It was 1995. People were tired, or maybe 98. People were tired of storing passwords and usernames in a flat file and having to reread the flat file every time. They needed a simple key-value store, and in this case, it happens to be a key-value store supporting compound static types for the values that it called rows. But it wasn't relational, and it solved people's problems just fine if they just needed a list of their users. If a document data store, something like MongoDB, or a key-value store fits your brain and behaves like you expect, then use it. Please, for the sake of Mike Baer, don't use a relational database because you think doing so is somehow right or noble. If you don't understand it, you don't have time to understand it, and you have a vain hope that your ORM will let you hide from how relations work. An ORM is a shortcut for a lot of things, but it's not a shortcut for that. Use a data store that fits your application, fits your data, and that you understand. And, as a hint from my own long experience, relational databases are awesome. SQLAlchemy is awesome. And of course, Python is awesome. Thank you very much.
We have time for 2 questions, if anyone wants to ask a question.
We did get a late start, and I see people already collecting along the back wall of the room. Come up to me afterwards if you have a question. Thank you guys very much.